All right, well, let's go ahead and get started. So this will be the last session. So we started when after the introduction session on the first day, we started looking at serial R and profiling. Then we moved to parallel stuff and all these neat examples through various groups and people. So now we're returning back to serial stuff, but with massive performance improvements. So I hope this will be a very useful session, because after talking to many of you individually, the impression I get is that a lot of people are already doing things in parallel, but not a lot of people are doing things in compiled code. So hopefully this will be very useful. So we're going to talk about Rcpp in particular. And I have a lot of things to say about what that is and what that means before we really get started. We have some examples. We have the usual toy example that everybody does when they do anything for some reason. A little bit more interesting example. It's not biologically motivated, but it was just too good to pass up. And then some extra things to close out the session. So what is Rcpp? Why would you care about using it? And the pros and cons of using it. So Rcpp is a package to make utilizing compiled code from R easier. Okay. It's also a package ecosystem, so there are multiple packages. Rcpp is the main one. There's Rcpp Armadillo, Rcpp Eigen, Rcpp GSL. It allows R to utilize C++ code very easily. There are multiple ways to interface to compiled code in R. So there are sort of two efficient ones. This is a layer on top of the real proper efficient one, making it the second. It contains lots of high-level magic to make writing C++ code for R, and I emphasize that, easier. So it is a way of interfacing R to compiled code, and I emphasize again, a way. It is a set of utilities to make writing C++ more convenient for R users, a tool which requires C++ knowledge to effectively utilize. So it doesn't absolve you from having to understand C++ issues, unfortunately. So it's not magic, unfortunately. This is the view a lot of people have of Rcpp. That's about as close as R gets to magic, maybe, but it's not magic. It is not an automatic R to C++ converter. You do have to actually do things yourself. It is not the only way to bring compiled code to R. It's probably most people's preferred way, but it is not the only way. It is not a way around having to learn C++, as I say. So it will not automatically make existing R code faster. You would have to rewrite that R code. And it's not as easy to use as R. It's the next best thing, maybe, but it's not exactly as easy to use. So recapping some things that we've discussed many times now, R is slow, and if you don't know what you're doing, it's really slow. Loops are between 50 to 100 times slower than native C and C++. On average, you can cook up examples where it's 20,000 times slower. Dirk, the author of Rcpp, he actually has an example like that, and it's amusing, but where it's literally 20,000 times faster to use the C code. But it's not like, don't expect that. R aggressively overuses memory, whereas in C++, the benefit, but also the major drawback is you are directly managing your memory. That's what the C languages are for. That's why C was made the way it was, and all the strange things it contains. C++ is something of a giant overgrown monster living on top of C, and so if one of the nice things about R is you don't have to manage your own memory. R does it for you. Well, it's also a drawback because it doesn't manage it that well, maybe. Other problems with R is single-threaded, and in fact, R is notoriously not thread safe. We don't really want to get into what that means, but you would have to be very careful when you're doing, for example, multi-threading with random number generation at the C level with R stuff. We won't get into that, but if you know what those words mean, then keep that in mind. So I really like this quote. I really, really like this quote. So this is Linus Torvalds, the fellow who created Linux and now maintains Linux. So he says, sometimes pi equals 3.14 is infinitely faster than the correct answer, and the difference between the correct and wrong answer is meaningless. That he says specious value of correctness is often irrelevant, but performance always matters. And This sums up my philosophy in life at the moment. I absolutely detest the fact that people often so quickly dismiss performance concerns. That doesn't mean you should, make it your priority to get the wrong, truly wrong, whatever that means in your context, the wrong thing fast. But you shouldn't just say, speed doesn't matter. I don't care. It can run for 100 days. Who cares? You really should be concerned with these kinds of things, because you'll quickly find what you're doing sort of made irrelevant, even if it is, mathematically, within the domain, biologically, a much more elegant solution. People are very practical. So you should care about these kinds of things. So you may say, well, why even use R at all? Why don't we just use C and C++? Just throw R in the garbage. There are a lot of great reasons to use R. It has the most diverse collection of statistical methods available. And that becomes more and more true every single day as more packages are added to the CRAN, for instance. R is great at rapid prototyping. So maybe your model becomes, we're going to develop something in R, we prove it, it works, and then we move to something else. Maybe. I don't know. Some people do that. As I say, the CRAN packages, the CRAN is a really, really, there's just no parallel. The CRAN is amazing. No other language has anything quite as good. And the syntax is designed for data. The R syntax has been around since the 1970s. It is a dialect of the S language from Bell Labs, from John Chambers. So, people have found value in it. It just has some performance issues. So, here's one thing you might do. This is a proposed development model. So you prototype in R. So you develop your method, you prove it, it works, it's great. You profile your method. You consider moving some expensive pieces to C, C++, and fortran. And then you might use R as a high-level interface for that low-level code. This is pretty much what I do. This is what I do for clients. This is what I do for PBDR. This is what I do in my own free time. This, I think, is a really good model. So why Rcpp? What are its advantages? Compiled code is fast. It's very, very, very fast. So there are lots of compelling reasons just from speed alone. Rcpp is, it's easy to install. Assuming you have a build environment set up, it just installs and it's fine. It's on CRAN. It's great. It's easy to use compared to other options available. It's better documented than many of its alternatives. So there is a native C interface for R. That is what we tend to use, and we have reasons for doing that. We don't use Rcpp, for example, in PBDR. We have good reasons for doing that, but the documentation for what we use is not near as nice as the documentation for Rcpp. It has a large, friendly, helpful community, and if you don't believe me, these are all the packages on the CRAN which either depend or suggest, I forget which color is which, Rcpp. So here's Rcpp in the middle, and these are all of the things that either depend or enhance or suggest or whatever the colors are, I forget. So there are a lot of people using the thing. Sure. Yes, I used. So that's a very interesting question. So if I don't mind saying so, I'm a bit famous on the internet. So not really, but I have this blog called LibraStats. I go by Mathematics online. So I developed a thing that would do this, and it inspired some people to actually do a much more clever solution. If you just look around for like R visualizing the CRAN, you'll find maybe the thing I did, hopefully the thing that the enhanced fellow did. But it uses iGraph. iGraph is a package. It's a C library, has Python and R bindings, and you can do these kinds of graph visualizations, network visualizations, and other kinds of network computations, by the way. So what are the disadvantages of using Rcpp? Well, it's C++, and I really do emphasize there be dragons. C++ is not my favorite language. Let's be polite. So I'll try to keep disparaging comments about C++ to a minimum, because those are a reflection of my own opinions. But even people who really love the language would say there be dragons. It's very difficult to debug and profile. So for example, using any kind of compiled code makes debugging and profiling a little bit harder, because all of a sudden rprof is going to bottle everything you're doing in compiled code into a .call call. And so now, how do you understand what's going on in the compiled code? Depends on how you've architected it. Debugging this becomes harder, profiling becomes harder. In general, C++ is just sort of known to be more annoying than, for example, C or Fortran to debug and profile, and this often comes from so-called template metaprogramming abuse. We won't get into templates. If you like them, good for you. Rcpp code must be GPL licensed, so maybe you don't care, but Rcpp itself is GPL. You link with Rcpp if you want to use Rcpp by the rules of GPL, therefore your thing must be GPL. Maybe you don't care, but it would have to be GPL. It is designed to only work with R. So if you develop a solution inside of Rcpp using Rcpp stuff, okay, if you use it as a wrapper for C and C++ code that's more generic, you could eventually take that out and move it somewhere else. But if you're developing strictly inside of that ecosystem, then you are stuck in that ecosystem. And decoupling from Rcpp would be difficult. I don't think that's a reason to avoid Rcpp at all, unless you have a very good reason to feel that, for you in particular, that's a reason to avoid it. But it's something you should be made aware of. It's something that gets minimized a lot. In the examples, we will be using the inline package. Inline allows you to just basically write your Rcpp code in an R terminal, basically as a string, and then you can compile it on the fly directly from R. So it allows you to easily build Rcpp code and interface to that compiled code. It is not a permanent solution. Don't even pretend that it is. It is not. It is meant for rapid prototyping and for, in this case, demonstration purposes. For a long-term solution, you should really be putting things into packages. And we'll see why, actually. How do you install it? We'll just briefly go over this. The slides are available at the usual places, at the NIMBioS WordPress, and then at the site where I've been posting my own stuff. Should be at both. So the package installation will require more work depending on what you want. For Linux, you basically are done. Everything works on Linux. I don't know why it gets this reputation. For Mac, you have to install Xcode. You may need to install gfortran if you're going to interface with Fortran. And then you can just install Rcpp and inline, and you're ready to go pretty much. On Windows, it's a bit more annoying. Instructions are pointed here. We're not going to go over them, but it's just a little bit more cumbersome. OK, so here's basically a hello world, which you could run. This is just R code. You just take this R code, and it's in the file that's posted online. And you could just source this, and it should work. You should be actually printing through the compiled code.
If you're using Linux.
No, this will work on any platform, assuming it's been set up correctly. So Rcpp is platform independent. It will work anywhere. Inline is platform.
If people are trying this right now, they would have had to do those steps.
Well, all of our stuff is available on the EC2 image, so you could connect to the one that we've had open. You could connect to the one that you set up yourself if you wanted to follow along. But locally, it would take some doing, perhaps. But you could take this, and assuming you had the build environment set up, you could just source this, and it would print something and then return a null. Okay. Documentation. Rcpp is very well documented. It has a sure.
So you don't have to include libraries, like if you use, for example, like vectors, C++, or something like that.
So STL comes along for free with Rcpp. Rcpp is very much in the STL ecosystem.
But you don't have to explicitly, like in C++ code, you have to not include it.
Sure. OK. So with inline, mostly not. When you're doing things in the proper way, you'll need to include rcpp.h. That will bring in a lot of STL stuff. Of course, if you're using some other external library, you have to bring in its includes. So a little bit trickier than we can handle right now, but that is a good point. It's a good thing to think about, but we'll see an example at the end where it's a little more explicit. So it is very well documented. It has like 10 vignettes you can look at. I would start with the intro. That sort of assumes that you are fairly familiar with how the internals of R work, in my opinion. So maybe start with that one even last. The quick ref and the FAQ are great. The quick ref is really handy. Hadley has everybody knows who Hadley Wickham is. He has like a wiki where he maintains a bunch of different things. One of them happens to be about utilizing Rcpp. That's probably the first place you should look to really understand how to get going with this stuff. We'll give you some good examples, hopefully, but probably there will be a few holes. You'll wonder, how do I continue? This is a good resource. Dirk actually wrote a book. It is one of those Springer use R books. So I downloaded it for free through the library. I took a look at it, and it looks pretty good, but I don't know that I would spend like $60 on it. But it doesn't look too bad. The documentation is a great way to get help. Stack Overflow has an Rcpp tag, and the people there are very friendly, so you might consider that. There's an Rcpp devel list, and it has a very different feel than the proper R lists. So they're very friendly, they're very helpful. So these are good resources if you are working on a specific problem and get stuck. Okay, so the basics. This is, every time you are using or writing Rcpp, this is basically how things will go. When you are interfacing with any kind of compiled code from R, there are two steps. You write the C++ code, you write the wrapper code. How do these look? So the C++ code looks something like this. So you're bringing in rcpp.h. You'll do rcpp export. This is basically just a quick define for extern C, if that's meaningful to you. If not, just remember you need to rcpp export. SEXP, all R data structures are really underneath their C structs. SEXPs are pointers to those objects. So you should just think of this as returning an R object, an R vector, an R list, an R data frame. Those are SEXPs. Okay, it's just a goofy name we give them when we're in C or C++. Then the name of your function, the arguments. Well, anything you're passing down comes from R, so those are SEXPs. And then you're going to do some stuff and return an SEXP, because this means I'm returning an SEXP. Okay? Now the wrapper portion, this is just R code. Okay, so you'll say, well, my function looks like function. Well, we said the arguments were X and Y, so maybe we have X and Y as input from the user. Whatever those things are, we're just being vague and abstract for the moment. So you would say .call, the name of the thing here, then the arguments, and there are some important things to know about those arguments we'll talk about in a moment. If you're using a package, you can specify that the symbol, my CSX function, comes from package, my package. I recommend you work with packages. And then, you're storing the result, you return it. This is just R. The only difference is how we use this .call to explicitly pass things around to compiled code. Okay? So you can make hello world very complicated. Here's how you might do it. This is self-contained. We just don't have a wrapper. It's basically the same as the inline one from before, but you do rcpp export. This just prevents C++ from mangling the name here. SEXP, because we're going to return an R object, the name of the thing. There are no arguments we're passing down. So rcpp rcout, if you're familiar with C++, there's cout. That's a sort of special thing. Rcout is R's version of printing to terminal, where terminal may not be a terminal. It may be a graphical window or something. So you should use that. Hello, then this is an inline. Return R under no value. That's just the null from R. and we're up and running. We're using compiled code from R. How would you compile that? There's a very bad way that I've seen people do. I don't recommend it. I can't call it the easy way because it's not easy, but it's better than this. The package way, which is not easy, but has many advantages once you're living inside of that frame of mind, and the inline way, which as we know is not a permanent solution. So the really hard way would be just to specify all of these include flags and library flags, and I've seen people do this, and it's crazy. You should not do this because this is the least portable thing on the planet. R actually keeps all of this information and this information known as long as you call rcmd shlib. Okay, so we're building a shared library. It's called. And these two are Rcpp specific things. And you could literally just copy paste these two lines, keep them forever, rcmd shlib on my source code, my various source code files, and that will build the shared library using Rcpp. If you don't want to recompile every time you start R, like you're really moving towards a permanent solution, away from inline, and you don't want to set up an R package yet, then this is the way that I would go, but I would really seriously recommend getting into writing R packages. There are a lot of advantages for maintaining your code in an R package. Sure.
So that's compiling the C++ code?
Yes, correct. Okay.
So you don't need and I'm not familiar with much of C++,
Mm-hmm.
I do need to use it. My understanding is that you need to buy an expensive several $100 thing to compile the software for it to do that. So I don't need to do that.
Oh, no. The instructions here, wherever they are. So maybe you're on Windows. Okay, so you're on Windows. Windows people are going to have the hardest time setting things up. So remember slide number 15. So this will get you set up and it won't cost you a dime. So there are free compilers and they're pretty good compilers. So it'll get you set up with the GNU build system. There are non-free compilers and they may produce faster binaries, but one step at a time. I would definitely start here. But this is all free, this is all free, and then that's all free. I would definitely start here. So doing this, assuming, and I'm using Clang, because Clang is my baby. I love Clang. Clang may be a little harder to set up on although on Mac it actually would be very easy to set up. On Windows, I have no idea. On Linux, it's pretty simple. But here, so we're building the shared library. We haven't talked about interfacing to that library. You would use .call, but then there's another piece. So I mean, there's a lot of upfront stuff you just need to be aware of. It's not that bad, and once you get used to it, it really is it's just not that bad. But this may be very new for some people, and I understand that. Sure.
Just a real quick question. I've never seen the three colons together there. I'm just wondering what.
So two colon is a namespace accessor. So RCPP : means I want to access something that has been exported to the RCPP namespace. 3 colons means I want to access a hidden thing from that namespace, something that was not exported. The reason why Dirk chose to not export these, I'm not sure. I have a guess, but I'm not sure. Just the fact is, this is sort of the code that you would want to do, because that's how he happened to set things up.
You can do that, I mean, just in your R code then as well. Is that, yeah, that's just R code, right?
Yeah, this is R code, so Rcpp-E.
Your own,
Yeah.
packages if you have something that's not exported.
Yes, of course. Yeah, so I mean, we hide things all over our packages. If you wanted to access one of those hidden things, you would use the 3 colon. Now, CRAN will yell at you if you use 3 colons inside of a package, but that's an entirely separate issue. So the package way of doing things, we'll return to this. We just one bit of complexity at a time. The inline way of doing things we've already seen. This is just a recap of that original example, that sort of hello world example. So this is self-contained, assuming you have that build environment and compilers installed. That will just run. And it should when you call this function, it would just print it works. So how do you call function from R? Oh no, I didn't mention dyn.load. I knew I was forgetting something. So that's very interesting. Okay, assuming you have loaded that shared library into R, you would use the .call function just as we have seen. Okay, so .call, the name of the thing in quotes. You can actually remove the quotes and put C underscore. That confuses me. I don't like it. I recommend you just put the name of the thing in quotes, then pass the arguments, the name of the package if there's a package. How would you have R have access to this function? I didn't put this in the slides, and I do sincerely apologize. If you're not using a package, if you are, it handles that for you. If you're not using a package, like if you're back here doing something like this, and it creates like rcpp under hw.so or .dll, from R, use the function dyn.load, dyn.load. And you do dyn.load on that shared object. And that gives you access to those functions. I didn't put that in, I apologize. Packages will handle the dyn.load aspect for you. Okay, so a quasi-real example. Everybody has seen this probably. You've probably seen this multiple times in multiple places. We're going to do a simulation where we estimate pi. How will we do it? We'll do it in R using loops. We'll vectorize it. We'll use C++ or Rcpp. We're going to benchmark it. And then think about some other things, maybe, other than just runtime. So here's the loop code. Okay, not a lot of interesting stuff going on. Maybe, you could, well, we'll get there. So this is a reasonable, I'm not intentionally trying to inflate benchmarks here. I think this is a reasonable approach if you were tasked with using for loops in R to solve this problem. Okay? Probably a more obvious choice from R would be to vectorize in this way. So I feel like this is fairly self-contained. Slow me down if this is going too fast. Don't be upset if it's too fast. I'm guessing you've seen this before. If I'm wrong, slow me down. This you may not have seen before. So what are we doing? We're using inline, and all of this code should be in that script that's available on the WordPress and my own place where I've been storing things. So cxx function is a special function from inline. And what it will do is it'll take a string that is actually RCPP code, and it will, with some other things like if we explain to it what the input arguments are and what plugin we want to use, more on that later, for now just RCPP, it will compile this function, make it accessible into cxx underscore pi. We don't even need .call. We just now call cxx underscore pi on whatever thing we pass in. Now notice it looks very similar to the for loop implementation here. Okay, it looks very similar. The difference is I'm using R's random number generation. That could be good or bad depending on your philosophy. Notice here I'm passing in underscore. There's a reason I'm doing this. Why don't I just call it in? And what is this? So I'm saying I'm passing down an integer. Okay. Do we need to talk about integers and doubles, or we're good? So we're passing down an integer. When I do this, RCPP as, when I say int, in underscore, cast that as integer in. Okay. That will, hang on, let me think. See, this is why I don't like C++. I have to think. I think that will produce a copy. I'm pretty sure that will produce a copy. So here we're copying the value that's here stored as in underscore to this integer in. So maybe this isn't actually a good way to do things, but you could do it. more on copies soon. So I'm pretty sure we're making a copy here, storing U and V. Each iteration of the loop has doubles. You know, we just have a little counter, return, wrap. Here I'm casting as a double, 4 times R over N. That will create a copy in a strange way that I probably don't want to get into at the moment. But copying data is an important point, which we'll have a better example of in a moment. I shouldn't have even brought it up. So this is how you would write and call that. Sure.
What is the wrap function?
The wrap function, great question. So Rcpp wrap takes like a C object, like int, double. R doesn't know what ints and doubles are. R knows what SEXPs are, remember. SEXP is an R thing, because R doesn't actually have ints and doubles. It doesn't have scalars. It has vectors of length 1, right? So if we want to return a vector of length 1, we'd have to go create it. This is a cute shorthand that Rcpp will just take this thing it knows is a double, turn it into an SEXP of the right type, and pass it back to R. Great question. Rcpp wrap will create copies when it needs to. It tries to avoid deep copies. Yeah.
Can you run any arbitrary R function in the C++ code with a colon?
No. So this is a special thing that he has set up. You can run any arbitrary R function from C or C++. And in fact, you can do it in some pretty surprising ways. That's pretty advanced, let's say. But it is possible. So let's benchmark the methods. So we load our benchmark. Sure.
Using the run if there, why aren't we using C++ code?
What do you mean? No, this is C++.
The run if is C++?
This is something that is from, okay. So R has a bunch of functions that are accessible from C, even if you don't use R. You could build C code that has nothing to do with R and compile and link it with R's, for example, random number generators. Dirk exploited this to create the ability to call R's random number generators in sort of a slick way. But this is C++. This is Rcpp, right? So, I mean, it looks pretty similar to this, right? Nearly identical, maybe. There are some, we're being explicit about type, and that's where a lot of the speed comes from. Actually, is just being very explicit about type. So if we compare these different solutions, we can see. So with 100 replications, n equals 50,000. The loop, the elapsed time was 35 seconds. Vectorized R code was a little under a second. Rcpp was a little over 1/10 of a second. So Rcpp 213 times faster than this. Now this isn't a really hard problem. In practice, I would expect to see much smaller gains than that. But it's 5 times faster than the vectorized code. Pretty nice. And we didn't have to work too hard to get it. Okay. Now, the harder the thing you need to do, the harder you have to work. So what about the compiler, I say? What about the compiler, the bytecode compiler? How will that change things? So I'm going to call CMP fun on all of these and store them as just some other name. Rerun it, and what changes? So the R loop goes from about 35 to 30 seconds. For completely free, that's not bad. I'll take it. But the Rcpp one doesn't change at all. You can see it's just what it is. The vectorized code, it gets slightly faster, not really a whole lot. But the compiler is completely free. There's no reason not to use it. It certainly helps these other methods, but Rcpp is still the clear victor here. So now we can really get a sense for just how good the compiler is versus moving to compiled code.
I know we already covered this, but just to remind me, the CMP fun you can use on any R function?
Any R function at all. And this comes from the compiler package. CMP_fun converts it to bytecode and just returns a bytecode compiled function which you would store somewhere else and execute like any other function. Okay. What about other concerns, right? Runtime isn't the only thing in the world that matters. In the real world, you have to be very aware of how much memory you're using. And you can put some asterisks actually on all of these. I'll explain what I mean in a moment. But for loops, I'll just tell you we're using 4n plus 3, where n is this n right here. 4n plus 3 integers and 8 times 3 doubles, plus some epsilon, not worth worrying about. Just some value that r is going to be inflating doing things. All of them have an epsilon. So this is why I say you could put an asterisk. So certainly no less than, put it that way. No less than this much. Vectorized will use a whole lot more, actually, especially as n grows. Rcpp is actually quite fixed. And there may be a little bit of overhead, like you may end up with an extra double or an extra int here or there, but it's pretty much fixed, actually. So as n grows, the amount of memory usage this is using is almost nothing compared to something that's getting larger and larger and larger. And this is faster anyway. It's clearly the victor. So a quick summary here for n equal 50,000. Here you can see the average runtimes, and here you can see the memory usage. Rcpp used on the order of 36 bytes compared to the vectorized solution that used over a megabyte. And it's faster anyway. So, and here's what I was using to do these benchmarks, so you could theoretically replicate them.
How did you monitor how much memory usage there was?
So I didn't monitor. I basically looked at the algorithm and counted. And this is why I'm not sure what that. I keep talking about like a fudge. I'm not sure what the fudge is. I know it's there for sure. It's especially there here. I'm not sure the order it would be here. Like I said, maybe a couple of doubles, a couple of ints. But this is just knowing what it's allocating, basically. Okay. So.
And that's because you generated all the random numbers first.
So like in the vectorized one, why is the vectorized one so bad, right? Why are we using so much space on the vectorized one? Because we generate, all the random numbers at once, and they are in storage all at once. Then when we do the row sums here, that's a new vector that's stored. When we do row sums less equal 1, that's a new vector that's stored. And then we sum it all up into a single value, the only value we wanted. So vectorization is quick, but it is very, very, very aggressively overusing your memory. Okay. So compiled code is faster than R. Nobody's surprised, probably. Vectorized code is better than loops, but worse than compiled code. We've hinted at that. Now we see in a very clear example the various ways in which that's true. Bytecode compiler helps, especially with R loops, not by a whole lot. And then other things it helps a whole lot less. R's memory footprint, as I say, is terrible. But do keep in mind that, I feel like this is a good example to look at, but most speed improvements will be more modest than this. They wouldn't exactly be modest. They would be on the order of 50 to 100x, probably. Maybe as low as 30. But still more modest than this, average case. In some cases, you might just get a very tiny speed up. And this is why you profile, to make sure you're not wasting your time. OK, so this is an example. Somebody contacted me. He was trying to parallelize some stuff, get it working with the PBDR stuff. We're not going to talk about PBDR here, but it's just such a great example of the kinds of mistakes you can inadvertently make when you're writing R code, the ways you can improve it, maybe move to C++. So I don't know of any biological application, but it's just too good of an example I couldn't resist. So cosine similarity from vector calculus, you can define this. And so then we can define a cosine similarity as just this quantity, whatever it happens to be, for these two vectors x and y. So if we want to form a cosine similarity matrix, a matrix of like all pairwise similarities, it would look something like this. The notation is cumbersome. The idea is simpler than the notation almost. This is the implementation in CRAN's LSA package for doing like latent Dirichlet allocation kind of stuff. So, which is where you would really be interested in this kind of question. So this is the code. And there are lots of things I don't like about this code. What do we see right off the bat? Do we see anything that might make me grumpy? So there's nested R for loops. That's bad. Do you see anything even worse, maybe? It's recursive. Don't do that. So not only is it recursive, but he's computing. So he's trying to minimize computation. If you look at the indices here, the upper ends of these indices. And we don't want to study this too much because maybe you couldn't care less about this. But as an example of looking at ways to improve computation from R, it is a good example. So he's trying to minimize the amount of computation that he's doing. But look at how much memory allocation he's wasting. Okay, because he's not being clever and storing things, right? So I here is ranging, and each iteration of j, he's reallocating x comma I. That requires a new grab of that column each iteration. That's terrible. Here you could maybe be a little more clever, but it's not the end of the world. This I just feel is kind of strange in general. We don't want to spend too much more time on it. And then he has a little catch to make sure you're doing things right. That's a very good thing to do. Here's my improvement. So he sends me the original code. He sends me his attempt to make it run with PBDR. And I look at the original for a few minutes, and I see some things I don't like. Here's how you might improve it just right off the bat. Is you can do a lot of these computations up front and be a little bit more clever with your memory usage. So talking about exactly why this is better is maybe not worth focusing too much on. But this is a much more memory efficient approach. I think it's roughly on the same order of computation. So I think we should be doing about the same number of computations, but I'm doing a whole lot less memory allocation and deallocation.
Quick question.
Sure.
So when you coerce 2 there to be an integer.
When I coerce
or you give it
2L.
Instead of 2.
Yeah.
If you just did it 2, would it actually return a range that was numeric rather than integer? So every time you subscripted something, it'd have to convert it back to be an integer?
Good question. So by default, R will turn that, assuming you give it something that looks like an integer. Like 1 is not an integer for some reason in R. So if you give it something that looks like an integer, something that looks like an integer, it will be a list of integers. Right. This is my way of making sure R is not doing what I don't want it to do. So I just get into the habit of, if I know it should be an integer, I put the L. It just makes it very explicit for me. Again, L for integer, which is obvious. So here's how you might naively do this in Rcpp, right? Here now we really do want to bring up the issue of copies. Okay? So I'm passing in CP underscore. I'm not sure why I named it that when I think about it. DG underscore, a matrix, a numeric type. Why am I naming them with these underscores? Because what I really want to do is access the higher level functionality of Rcpp. Rcpp has things called numeric matrix, numeric vector. It has integer matrix, integer vector. These are useful abstractions, and I can create so-called shallow copies. I'm not actually copying data when I say CP contains all of the data of CP underscore. I'm adding an abstraction layer on top of that data to allow me to be able to do things like this, which looks mysteriously sort of like R code. Notice we're using parens instead of brackets. They're basically stuck that way because bracket means something else, and dispatch. So even with C++ as object-oriented programming, you can't really fix that, but it is what it is. So these are shallow copies. When you do something like this, okay, as long as the types match, a copy will not be produced. So you can safely do this. This is something that doesn't get broadcasted a lot. And it made me very wary of RCPP the first time I saw it. I thought, what? They're doing all this copying. They're crazy. You're probably not doing copying. It will produce a copy if it needs to. That's RCPP's philosophy. They'll do what you ask it to do. And it tries to do that as efficiently as possible. It's a good philosophy. But as long as you pass in a numeric matrix here, when I cast RCPP numeric matrix, it will not create a so-called deep copy.
And that's different than the as.
Yes. So the as caster that lives in RCPP is useful for if I wanted to turn this into like a double star. Double star, right? Okay. So here we can allocate the return. So we're explicitly allocating now. When I say RCPP numeric matrix, now it's the exact same call, only instead of giving it an SEXP, I can give it numbers, and it will allocate a matrix of that size. So it's pretty handy. It tries to look like R. It does some ways more than others, but we're basically just doing the same thing here as we were doing here. Okay. So I tend to think about the way things would look if they were efficient once you move them to compiled code. That tends to be a good way to do things in R sometimes. Vectorization is the caveat there, but then it's easy to translate this into something like this. So you could digest it a little bit more if you're really interested in the design pattern. It's not that interesting, and it has no real biological application that I'm aware of, but it's just such a good example. When we see the timings, I think you will agree. The last little bit, so we take the cross product. Oh, that's why we called it CP. I was thinking copy. CP is the cross product. So we take the cross product, we take the diagonal of that, we pass those two things down. That fills something CO, which we return. Okay? You could be a little bit more efficient in how you do this, not by a whole lot. So it, rather than explicitly computing the cross product, you can basically just skip some of that work and fill in copies. It turns out to not matter much, as we will see. So here I ran this up on Darter. Darter is where I tend to run things. Supercomputer at the University of Tennessee. So for various size matrices, this is the relative performance on, I think, 20 replications using our benchmark. So cosine was the one from the LSA package. This was my suggestion to modify. This was the first RCPP one, the fairly naive, just copy of this, translation of this to C code, and then this was the improved one. You can see the improvement, especially as things get larger, actually tends to diminish. It still is better, but not by a whole lot. Whereas, we're still doing a whole lot better than the original, but even my slightly improved one does okay, right? So, a 4x speed up going to C code, is that worth it for you? Are you at the order of a few minutes or a few days? Maybe that would change your opinion. So you just really need to understand your own personal situation in deciding what of these kinds of things you want to do. Again, what about the compiler? What does that change? It changes a little, not really a whole lot. So this one actually does a whole lot better. This one you can see a little bit better. This one is basically the same, and then this is still the winner, just not by a whole lot. Okay. So the compiler, the bytecode compiler, is free speed up. You should always use it if it makes sense, but it's not going to be as good as moving to compiled code as we see. It's much better to use compiled code. Okay, so the RCPP ecosystem. There are other things. We're just going to talk about these two. There's also RCPP Eigen. I think he even has some stuff for Boost. I think we have a few C++ programmers around here that may interest you. So Armadillo is a high-level C++ matrix algebra library. So the syntax for using BLAS and LAPACK is ancient, and most people don't enjoy it. Armadillo is just a different face for using those things. Well, you can use that syntax directly with Rcpp code using the Rcpp Armadillo package. And that doesn't require a system install or anything. You just install this package through the CRAN, and you have everything you need. You're ready to go. And I'll just show you a really quick example. Here, if you wanted, for some reason, to do the so-called outer and inner products, store them in a list. This is the T-cross prod and the cross prod. For some reason you want to do that, I don't know. Here's how you would do it in R. And then here is the C++ stuff. So now another use for as is casting to these other different kinds of, so there's an ARMA he's created. So Armadillo has its own matrix thing. This too is a shallow copy, unless it needs to be a deep copy, basically. But notice v times v dot t, open close paren. If you're familiar with C++, that probably looks very friendly. If not, this is just taking the transpose of v. Times, this is just matrix product. So that's how you do it. That's the syntax. It's pretty nice. If you want to do it the other way, v dot t, open close paren, times v. Looks fairly simple, right? And it works. How would you return a list? So far we've been returning fairly simple things. So Rcpp has a thing list. We can list create. We can give names to them just in the exact same way as I would say outer equals. Here I say Rcpp named outer equals the thing, the ARMA matrix op. And Rcpp knows what to do with those things. Rcpp named inner equal this thing here. And it really just is that simple. You go ahead and use it with inline. You could take a matrix, run all.equal f g at x, and you should get back true. So doing the same thing. Okay? I don't know that you would expect to see this to be really much faster, maybe a little just because of how memory is handled or something, but this is just an example to show off the syntax. So if you're doing linear algebra things in C code, you don't have to keep hopping back and forth to R. You could use, for example, Armadillo, which is pretty nice. GSL, probably I would think you've heard of GSL. This is a GNU Scientific Library. It is one of the biggest collections of numerical routines. It's almost certainly the largest free collection outside of mega collections like the netlib. But as a single library package, it's probably, maybe Boost, but it's on the order of Boost, let's say. Thousands of functions, has numerical integration, things for solving polynomials and interpolation, fast Fourier transforms, random number generation, has all kinds of stuff. And there's an Rcpp GSL package, so you can directly, easily work with GSL stuff. Pretty nice. High-level access to GSL, and again, it's through R. So if you're living in this land, you are building something that will not live beyond R without some decoupling effort on your part. Maybe you don't care, and in that case, this is a good strategy. And it plays well with the rest of the ecosystem. I don't know if I mention it here, but here you actually require a system installation of GSL, which is maybe a little trickier, but is possible. Otherwise, Rcpp GSL is on the CRAN and available. GSL is a really pretty nice thing, although back to the GPL comment, this is the GNU Scientific Library, and it is GPL probably 3 by now licensed. So if you use it, you're living in GPL. And here's an example that I just stole directly from Dirk's webpage. It does linear algebra. So one of the other things GSL does is linear algebra. Not quite as well as Armadillo, in my opinion, but here we're just doing some basic linear algebra. So here we're using GSL's wrapper of the BLAS, which uses the D norm too, so we're computing like norms, and you could run that. The example is in the script. You could take a look. This is fairly specialized. I don't really want to spend time on it, but it exists. Okay, so now one of the most important things you could do is to start putting things into packages. If you expect to use your code after that day, if it goes beyond maybe 200-300 lines of a single script, I would say consider using a package. If you're using compiled code, you really ought to consider using a package. That said, we won't be getting into CRAN issues because the CRAN is its own beast, and they have very strong requirements. Some of them they don't bother to tell you about. Getting things on the CRAN can be annoying. Getting things onto the CRAN when you're using compiled code, it's just a fact of life. It is annoying. And Rcpp can actually make things worse because I think it still doesn't work on Solaris, which makes one of the maintainers upset at you for daring to not support Solaris. So be aware of that. So here I've tried to visualize, if you're just working with R code, that's pretty easy, right? If you just have R code, put it in a package, it's easy. It's not hard. A package with your own C++, C, fortran, Rcpp code, that's harder, but it's not too bad. If you need external library code, now you have to be fairly aware of auto tools, and that's harder. Nobody likes it. Now, getting these things on CRAN is another story altogether. That's much harder. And I provided a visualization of how you get your packages on the CRAN. So it's not pleasant, let's say, but it is worth the effort. So some tools to help you create a package. R has package.skeleton. If you've never created a package before, maybe just run that. You just pass it a name, and it will create a directory with a skeleton of a package, and you can look at what it expects of you. Rcpp has its own that has just a few more things added to it. R code goes in an R subdirectory. Compiled code goes in source. Help goes in man for manual. Other directories, maybe you have an installation thing, something that should do something on install to the root of the install. There's a vignettes directory, a data directory, and they all have special rules. And
package.skeleton does what? It creates that structure. It doesn't put the source code in there. So you would
right. Yeah. It just creates a skeleton of a package so that you can go look and see what is the basic structure that is expected of you to have an R package that will build with rcmd install.
Okay. Cool.
And then this is just Dirk's. He added a few more things to it. If you're living in R packages, especially if you're using compiled code, a dense but absolutely invaluable resource is the Writing R Extensions manual. If you printed this thing, you would be dooming an entire tree probably, but it is a really, really, really comprehensive and useful guide. And generally the questions you want to ask, the answers are in there. And if you do ask R for help, they'll probably just yell at you and tell you to read this anyway. So it's a really, really great resource. The DevTools package, it has its uses when you're developing packages. It has some, unloading packages is sort of a messy process in R. He has some utilities for that if you want to maintain a single R session while you're, you load. So you install, you load, and you don't like it, you unload, you install, you load. It makes that process a little bit less painless. It has other uses, of course. So this is just sort of a wrap-up, I guess. So you put the R code in R, compiled code in source, and make vars, which is the annoying piece. God help you a configure.ac if you need it. If you're linking to external libraries. You can use CMake, and I love CMake, but CRAN offers very limited support for CMake. I don't know that they will build Windows or Mac binaries if you use CMake, but CMake is awesome. Maybe they'll change their mind one day. So make vars is an R package's bizarro version of a make file. And if you are familiar with auto tools, it'll look mostly familiar with a few strange changes. If you're not familiar with auto tools, I would really recommend you just go find some other package and look what they have done. Maybe even ask them for some help. Nobody likes auto tools, so we all struggle with it and we all understand. So I would say, don't be afraid to ask questions and just look at what other people are doing. It's usually not too complicated unless you link with external libraries, and then it's just a huge headache. The R-devel list is available, but the usual warnings of, make sure you you ask the right question in the right way, that kind of thing. When you're using Rcpp, these two things belong in your make_vars file. And as long as you do that, the rest of it should be fairly simple. You could literally just copy paste that, and that's all you would need to know. You just need to know that this is a special thing for being able to know what pound include rcpp.h is. This is for linking with the static library for Rcpp. If you don't know what those mean, it doesn't matter. You just copy paste that and it'll work. Quick wrap up. There's a lot of stuff we didn't talk about. So this again is kind of a broad overview, just sort of explaining options available, a few examples, hopefully priming all the right pieces so that you at least know what to go search for. Getting an Rcpp using package onto the CRAN is just an entire beast unto itself. It's just hard and will take time. Embedding R in C is possible in various interesting ways. You can link with the math library of R. You can actually build R as a shared library itself and call R. That is not very well documented. So Dirk created this thing, or he was part of a team who created this thing, R inside, which makes doing that kind of thing much easier. Bringing fortran into the mix really complicates things, maybe, depending on, because you're probably using external libraries if you're using fortran, and then that gets hard. Threads and MPI together from compiled code we didn't talk about. That's another huge headache. The choice of compiler, we didn't really get into how you would change compiler. There are various ways to do that easily and in more difficult ways. You may be interested in Rcpp attributes if you're already using C++ and you're just learning how to integrate it with R. That probably will look more comfortable to you. I think this is the devil's business, and I don't trust it. So, but C++ makes me nervous anyway. So take that for what it's worth. We also didn't talk about maybe the most important thing: tabs versus spaces. The correct answer is provided. So if tabs versus spaces in your editor. So that's all I've got for Rcpp questions. Sure.
Okay, so the devil's business is the Rcpp attributes, you're saying?
It's a very C++ kind of solution to make. Maybe you look at like Rcpp export, SEXP, da-da-da-da.
Yeah.
Maybe you see that and go like, well, that's a little kludgy. If you do, maybe you think more like a C++ person than a C person, and in that case, this is the thing for you. Whereas I sort of want to be very explicit. I'm more of a C person.
Yes.
So, there was another question?
Tabs or spaces you mean in your R source?
In your editor. I'm basically joking. But yeah.
So you mentioned a couple times that it makes a really shallow copy. It's basically like wrapping something over a pointer.
Yeah, basically.
Yeah. So unless it has to. Unless it has to. When it has to, is that because the object you're passing in from R doesn't have quite an equivalent or something in the...
So suppose...
It's not when you modify it, necessarily.
No.
Right.
So no, we're correct.
And there are some funny things, right, as far as, because of the copy on modify stuff,
Sure.
You can assign something to another variable in R and then pass the original one into a C function,
Right.
and then it will change the other one in these weird ways, right?
So let's hop back to something simple. So let me first start with, like here, we're creating shallow copies. When would it need to create a copy? Numeric matrix means the underlying C data structure are doubles. Okay? If you pass in an integer, it will either crash or create a copy.
Gotcha.
I think it creates a copy. Maybe you're lucky and it crashes. Now, there are other issues where you, for example, if you pass in, so here we allocated a return. And so maybe you get into the situation where I don't need a return. I'll just replace the data. That's dangerous. Don't do that. Because R functions, here we go. So R functions, if we pass in X, if we are sneaky and we modify the exact memory of X, we will run into trouble when the garbage collector goes looking for things to throw away, and it will just magnificently crash the R session. Don't do it. So that's a little bit more advanced, but you can get into lots of trouble by modifying. Because in R, if I have function and I send in data x, no matter what I do to x inside that function, outside the function, x should be the same as it was when I passed it in, right? There are a few very, very weird ways to get around that. But basically that's true, right? If you try to break that behavior with C code, you'll run into problems. I don't recommend trying it.
So you say just never modify a dereference pointer in C++. Okay, I mean, so never like don't modify anything that you've passed into a C++ function. If it was an R object.
So Rcpp makes that complicated. That's my philosophy. There may be like a syntactically more pleasing way. Like maybe Dirk is really clever, and sometimes he can understand and make a copy, and then you're fine. But I would maintain that philosophy. Yeah.
I was going to ask a question too. So is that like passing by reference? Is that something bad?
So no, pass by reference is great. In fact, so here when we're hopping down, like where's a better example? We have to go back. Here we go. So we have to go back here. So SEXP, that is a pointer, okay? And pointers are sort of dangerous. They're direct locations in memory, right? And C++ really tries to avoid ever really having to deal with pointers. Still being a C language, I find that strange. But here we're not. If we pass an object x into this function, we're not actually literally passing the object. We're not passing the values of the object. We're passing a reference to the object. When this right here would be, okay? R does not have, and here it gets complicated because R kind of has pass by reference unless you modify, and then it's pass by value. But so R is complicated. Here things are a little more explicit. If you pass a pointer, you're just passing the value of the pointer. You're not passing the thing it points to. And so this is why I say RCpp does not really absolve you from learning the intricacies of a C-like language. It can really get you going faster, and it can help you with rapid prototyping, and the inline function makes things easier. But for a larger, more complicated solution, you really need a good book on C++, I would say. Any other questions? All right, well, thank you.